Alright, so here I am in the second video because of spacing issues. So for the composition of microalgae, it's interesting because it has 40% lipids by mass, while soybeans only have about 20% lipids by mass. This means they take up more land to produce the same amount of lipids, soybeans. So soybeans conflict with the food versus fuel debate because soybeans can be eaten and are eaten in widely. So on the right here, the graphic, you can see that a lot of it is lipids at 40%. Protein is 30% for food, and carbohydrates 20%, and residual is 10%. Other uses for microalgae, as I touched on before, the residues left after processing can be dried and then be sold as pharmaceuticals, health foods, food coloring, fertilizer, bioplastics, or animal feed. One of the methods of cultivating the microalgae is open raceway ponds. There are the traditional raceway ponds that look like a race car track that go in a long circle. There are circular ponds and unstirred ponds, and they're all open to the elements and to sunlight. Open raceway ponds are the cheaper way to farm microalgae compared to photobioreactors. These systems are shallow ponds with a paddle that circulates water and algae throughout the structure. The algae on top is exposed to sunlight and carbon dioxide. The paddle circulates it all, so the algae has access to these resources. It is harvested in small quantities to be further processed. So on the other hand, there are photobioreactors. There are different kinds: plate, tubular, annular, and plate airlift. They are closed structures as opposed to the open structures that are the open raceway ponds. So one of the downsides is that photobioreactors are more expensive than open raceway ponds. They are a more efficient use of space because they, as you can see from the picture, they're all stacked on top of each other, yet still exposed to sunlight. They have better control of culture conditions because they're not left out in the open. There are no contaminants, which can be a problem with open raceways, like there might be just bacteria that could get in, or fungus, or even other kinds of microalgae that you don't want in there. For my data analysis, I collected data from different academic articles looking at techno-economic analyses of microalgal biofuels. So each study concluded that microalgal biofuels are still not cost-effective, even if scaled up. They are very much still in the R&D phase. They cannot compete financially with fossil fuels as of now. The different studies will be discussed on the following slides. So Nagajan et al. Conducted a techno-economic analysis, or TEA, on microalgal biofuels. They looked at improved cost estimations and optimized processes. They used government databases, quotes from vendors, and latest process improvement. They concluded that costs of biodiesel are around 42 cents to 97 cents per liter. They say single-step biofuel production is close to a commercial reality. Rashid et al. Conducted a techno-economic analysis on algal biofuels in the United Arab Emirates. They focused on open pond systems, photobioreactor systems, and two types of microalgae: freshwater algae and brackish to saline algae. They found that open pond systems performed better than photobioreactor systems by reducing more than 25% of the energy consumed and approximately 70% of the greenhouse gas emissions. They also found an 80% reduction in capital expenditures, or CAPEX, and a 40% reduction in operational expenditure, OPEX, for open pond systems. Davis et al. Conducted a TEA of open pond systems and photobioreactors. They concluded that in order to get a 10% rate of return, selling prices were found to be $18.10 per gallon of photobioreactor production and $8.52 of triglycerides for open pond production. They found that hydrotreating did not add significantly to the cost at $20.53 per gallon and $9.84 respectively. However, petroleum diesel has the production cost of $2.60 per gallon. Amer et al. Conducted the case study entitled Techno-Economic Analysis of 5 Microalgae to Biofuels Processes of Varying Complexities. Amer et al. Found that the traditional open pond growth system that uses shallow ponds covering large areas was the least expensive method for producing algal biofuels at an industrial scale. The drawback that added cost to this method was the price of solvents needed to extract the algal lipids and the necessary recovery of the solvents. This contributed about 30% of the $7.50 per kilogram production cost for the open pond method. Taylor et al. Looked at 4 combinations of algal biofuel technology components. They analyzed the operated expenditure OPEX, associated capital expenditure CAPEX, and revenues. The cheapest production route was a single-step extraction. This means extracting biomass from lipid and water from biomass simultaneously. They say bigger plants are needed to lower the biodiesel price. Further developments will come along with time as suppliers test their equipment on a larger scale. So for legislation, there is federal funding in the form of legislation that has been introduced in the House of Representatives and the Senate. In the House, H.R. 3249, the Financing Our Energy Future Act, has been introduced. Its companion bill in the Senate, S. 1841, has also been introduced. If made into law, this legislation would fund more algal biofuel research and startup companies. Another bill that has been introduced in the Senate is S. 1128, the American Opportunity Carbon Fee Act of 2019. This bill would tax fossil fuel companies based on the amount of carbon they emit. It would affect algal fuels by taxing them as well for their carbon output. If passed, this legislation may hamper funding and motivation for algal fuels because of increased cost. So with the Renewable Fuel Standard, we've discussed it in class, so y'all are pretty familiar with it. So in December of 2019, the EPA passed the 2020 Renewable Fuel Standard, dictating the goals of the U.S. to require the implementation of biomass-based diesel, total renewable fuel, advanced biofuel, biomass-based diesel, and cellulosic biofuel. The RFS also applies to microalgal biofuels. And here is a chart of the final volume requirements from RFS. So proposed action, funding for algal fuel research and development could come from local, state, and federal government. Private institutions can also donate money for further R&D, which has already been done. And the authors of the studies used in my data analysis agree that further R&D is needed to make microalgal fuels cost-effective on the market with fossil fuels. My conclusions and thoughts are that algal biofuels are not commercially viable yet because they are too costly. However, developments like downstream processing technologies, drying, biomass harvesting, and more advanced photobioreactors will make them more cost-effective in the future. And here are my references. Thank you.